Alright, last one, Newton's third law. Probably the most misunderstood law in all of Newton's laws. I mean, even Newton's gravitational. This is the most misunderstood. People are constantly quoting this law with no real understanding of what it means. Okay, so Newton's third law, the abbreviation I'm going to use is NL or N3L. Seems pretty logical. I go Ni or N1L, N2L, and 3L. Pretty straightforward. Newton's third law first states that whenever a force is exerted, there's an equal and opposite force exerted back. Now, everybody can quote that. Anybody. I go in and I start class and I say, all right, give me what you know about physics, and I undoubtedly get at least a dozen people that can quote that law, but none of them understand it. Okay? First thing, every time a force is created, it creates itself in pairs. Okay? So if I talk about a force, and one of the forces that we'll talk about is gravitational force. Everybody's experiencing the force of gravity. Okay? So I have an object. That object is feeling a force, the force of gravity. We also refer to it as weight. So it's being pulled down, okay, by the force of gravity. Now, I've went ahead and I don't want this object to drop to the earth. So what I'm going to do is I'm going to put a table here. Okay? I'm going to put a table here. So here's my table. It's sitting on that table. So it's being pulled down. It has to have a pair to it. And then I say, alright, so it's sitting on a table. What's its pair? Everyone tells me what its pair is, and they always tell me what the wrong pair is. Well, if it's sitting on a table and it's being pulled down by the force of gravity, that means that the table is pushing up on it. Right? Wrong. That is not its pair. Okay? When this object is being pulled down by the force of gravity, its pair is the exact same type of force. It's the same type, it's the same size. The only thing that's different is direction. Okay? So, if this is being pulled down by the earth, and I'm going to actually use a different colored marker. So, if it's being pulled down by the earth, here's my force of gravity. If it's being pulled down by the earth, which we all say from the force of gravity, that means that we have a really huge blue ball, which I drew in green, that's being pulled up by this stone with the exact same amount. Okay? That's a pair. Same type of gravity, or same type of force. Gravity is pulling the stone down. The earth is being pulled up by gravity towards the stone. That's the interaction there. Okay? But wait, you will tell me that doesn't make any sense. That means that this object is moving up with an acceleration. It's experiencing a force. So, going back to Newton's second law. Net force equals mass times acceleration. Using the first term, the first definition. Net force. The net force of this stone is how much it weighs. Think of it as weighing maybe 1 Newton, which is about the mass or the weight of a remote control. Or an apple. Or it's a really big rock, so it's a boulder. So let's say it weighs 1,000 apples. Okay? So that's how much I would have to exert to keep that object up, about 1,000 apples. Now, if I took 1,000 apples and I threw them down at the earth, will the earth move? Yes, but a very small amount. That force is 1,000 apples, 1,000 newtons, okay, on a tremendously massive object. Kilograms. Its acceleration is very, 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 very small. Doesn't experience much in the way of acceleration. It's a tiny value. So it does accelerate, but it's so small that you would never, ever, ever, ever notice it. Okay, we talk about, I undoubtedly get this question, what would happen if we got everybody to cohabitate in Kansas and then jump at the same time? There would be an acceleration. It just happens it would be very, very small. The entire biomass of the human population is pretty small, all things considered, compared to the overall mass of the Earth. So sure, it would accelerate, but not with any great amount. Okay? So that is a pair. Now where is the pair to this? Well, if the table pushes up on that rock, that means the pair is the exact same force, just in the opposite direction. So table pushes on rock, rock pushes on table. That's how the pairs work. Table on rock, rock on table. Rock on earth, earth on rock. That's a pair. Okay? Same type of force, same magnitude of force, same. The only thing that's different is directions. Okay? So when we talk about Newton's third law, first thing you got to realize is that forces are in pairs. The second thing we got to talk about is that there are two objects involved. Okay? Rock, earth, rock, table. Rock, table is one set of objects. Rock, earth is another set of objects. There's two objects there. Okay? Both objects experience the exact same amount of force, just in opposite directions. So the forces come in pairs. It has to have two objects in the system, and the objects are experiencing the exact same size of forces, just in opposite directions. That's Newton's third law. It's a brilliant law because there's other things that are happening in that with Newton's third law that makes things interesting. But rock on earth, earth on rock, rock on table, table on rock. Those are my pairs. Okay? If I have a submarine in the water, okay, the submarine is still being pulled by the earth. The earth is being pulled by the submarine. Water is pushing up on the submarine. The submarine is pushing down on the water. Okay? Those are my water pushing up, submarine pushing down. Those are my pairs. Okay? Submarine, earth, earth, submarine. Submarine, water, water, submarine. Okay? That's how it works. But that's Newton's third law. Okay? What I want to do really quick is talk about impulse. I'm going to go over impulse, and then we'll talk about conservation of momentum, which comes out of Newton's second law and third law. When we apply both of them together, we get this idea of conservation. And then what we're going to talk about is classical forces. Okay? So that's Newton's third law. It's a misunderstood law. If you can get a handle on Newton's third law, good for you. Okay? Because even teachers that teach science don't understand Newton's third law well enough to teach it, in my opinion. Okay? It's a really important law, but it's often misquoted and misunderstood. Alright? Cool.